As humans, we've always strived to create, to build something that will solve a problem or meet one of our needs.
How would you feel if you could hold some of your designs in your hand and they went like, that's impossible? And I said, well, let's assume it is possible.
I'm not a designer, but now that I'm seeing the possibilities of this technology, you start to see the world differently and you start to reimagine the objects around you.
There always seems to be someone on the internet decrying the lack of applicability of complex mathematics taught at the high school level. Some great points are made about how everyday things such as balancing a checkbook, applied addition and subtraction, are not specifically or properly taught to students, but that doesn't mean this kind of advanced mathematics lacks applicability, just that it's not common in everyday life such as, say, calculating the tip of a meal. One of those things that probably seems unimportant and unnecessary to students is integrals, but double and triple integrals and multivariable calculus are essential to additive manufacturing, better known as 3D printing. Granted, however, the math behind additive manufacturing is a touch more difficult than the calculus taught in a high school AP level course, but with a basic understanding of the math concepts in a CAD, which stands for Computer-Aided Design, or an API, which stands for Application Programming Interface, essentially anyone can begin crafting 3D objects. Okay, before we get to the math, let's go over a condensed version of the history of additive manufacturing. 3D printing was first invented in 1979, believe it or not. However, commercial printing machines that produce plastic prototypes didn't come into the market until the mid-1990s. 3D printing in itself has a number of different processes and means by which it produces 3D models. You can print in metals, you can print in plastics, you can print in photopolymeric materials, which are materials which are hardened with light. You can even print in ceramics, which is especially useful for making ceramic prototypes, because it doesn't come with the usual constraints of industry. What this translates into is giving the impossible a physical form.
Alright, so this segment of the video is going to be about the math behind Fubini's theorem. And Fubini's theorem can be simply tied with volume, much like the Riemann sum can be tied with area. And the whole idea behind Fubini is that you take these 2D slices and you layer them on top of each other so that you have a 3D object. So the double integral starts like this, and it should look very similar to the Riemann sum and the 2D partition. As you can see here, this is a rectangular region with another region inside, and our boundaries are from x equals a to x equals b, and for the y in the horizontal, we have it from y equals c to y equals d. So now that this region is divided between the k and the x and the y and the j and the y, the beauty of Fubini is that k or j, they don't have to equal each other. The partitions on x or y can be both different. The space between the k minus 1 and the k is just delta xk, and the space between j minus 1 and j is just delta yj. And then also, since we have to pick some point, we can pick some arbitrary point p or star or however you want to denote that. I'm just going to put p in the top left. I'm going to label it xkj star and ykj star. And that's what p is, some random point that we picked. So we know that this region is very tiny pieces, and the x-coordinate is denoted by x subscript k, and the y-coordinate is y subscript j. And like the Riemann sum of one variable, we have an arbitrary choice, as I said before, from each of the pieces as a random point that we'll be focusing on. The y increment is denoted by delta y subscript j, and the x increment is delta x subscript k. Essentially what we have in this picture is many tiny pieces inside this rectangle region here. An important thing to note is that the height and the width of the rectangle isn't the same at all. And I'm going to keep stressing that. because these rectangles are supposed to represent highly irregular partitions, 2D partitions of some 3D objects. It's with all of this free choice that makes this theorem very powerful and allows you to have sort of a wide array of what you can make in 3D printing. Once we have those rectangular domain partitions, then we have a choice of points for each of these tiny rectangles, and we evaluate those points with this function f. So function f of our point, so f k x kj y kj. So we compute the volume of a relatively tiny rectangle that we've chosen to draw as much larger than the actual scale, and now we can actually draw what that little 2D representation of the rectangle is, and it's essentially a cube, if you will. And obviously we have our function f of k, x, kj, y, kj, star, and that goes top to bottom. And then we have delta y, j, and delta x, k. And we have, with this and the summing up of all the volumes of these tiny building-like objects, if you can imagine, each point we pick, right, so let me put the point down. Each point we pick turns into these tiny buildings that go up to reach some height of the function, and they would all come together to reach the limit. So here in this picture we have some function that makes this sort of curve, and we have the miniature building that I drew. And the buildings that I was drawing, well, we'd have multiple buildings, all with the squares. Each square represents something that would come down. So right here we'd have a building, and then here we'd have another building. And all these, the 2D square that I showed before turns into a 3D rectangle as you put these parts together, and then as you can either lay them going from the x-axis, or you can do it from the y. Then you keep putting them together to reach the ultimate height of your function, and eventually you get this 3D objects. So working off of the Riemann sum and the general equation from that, we can get that it's the sum of, and then I'm going to put k first, k equals 1, n, right, and then sum of j equals 1. They don't necessarily have to be the same. There are two instances of k and j, and the number of partitions, and they're the number of partitions on the x side, k, and the y side, j. But because they're different, I'm going to say k with n, and I'm going to do j with m, because the partitions aren't the same. And then we have the function f of k of x of k of j star, y of k of j star, and then multiplied by delta a kj, which the delta a kj is gotten from the product of delta y j and delta xk shown before. An important thing to note and to point out involved here is not just that n and m are approaching infinity, but there's a choice of partition, and we divide the rectangular region, this one right here, and the one shown before, into these tinier and tinier pieces, and the way we do that is completely free as long as they get smaller and smaller. And the choice of these points inside are different. You need to choose a specific point to focus on, but that point can be chosen at random within the partition. So you also have a choice of point and a choice of partition. And for all these choices, we are considering this limit. So the final bit over all these choices is v, right? So it goes towards v. And we have that sum of k equals 1 and sum of j equals 1
nm f of x of k of j, y of k of j times the delta A goes towards double integral of the region R f of x of y dA. So now we have to understand that this double integral R f of x of y dA only exists if the function f is continuous over this region R. So the standard proof of Fubini's theorem is given for this continuous condition, but for my own sake and for yours, we're going to stick with a continuous partial because the arguments for the proof are for if we're doing a continuous or for calculus higher than like the college levels of 1, 2, or 3, and I'm not really sure we want to get into that too much. To go about this, we're going to look at an example for which the double integral doesn't exist. And we have to pick something that has a denominator, because normally that's where the culprit is the denominator. So we're going to go with double integral region R. I guess we could do x minus y, because if they're the same, you'll have 0. And you could have x plus y cubed dA. So this doesn't exist, right? And the picture for this, we'll do a little, pretend this is on an xy graph. I'll even put the little x and the y. We have a line of reflection, y equals x, and we have this arbitrary point. We're going to say that's AB, and this is BA. And this box goes from 1, 0 to 0, and then from 0, 0 to 0, 1. Right, and we also have this line right here. It should actually cross at the origin. This line, that y plus x equals 0. The rectangle we are looking at, which should look familiar, if I put this little box inside, it looks like the rectangular region from before. The only intersection on this box is at the origin with the line y plus x, and that's right here at the origin 0, 0. Notice here for the 2 points I've labeled AB and BA, for these two, the function value is the same except for the sign. So the beginning of this definition of the double integral starts with the Riemann sum. And the Riemann sum, the first part of it is the partition of this rectangle. So we're going to have to choose one way of partitioning this box. And method 1 would be a usual uniform partition, right? Which means that the horizontal and the vertical will be divided into the exact same length. And we're going to choose a point for each of these tiny square parts that we make, right? And we're going to use the midpoint rule, which you should remember from when we first learned the Riemann sum, which instead of taking the left bound of the right, you take exactly in the middle. So the general idea is that one way of breaking this up uniformly is we take that y equals x line and we create a box off of that line focused on a certain point. And then the point over there, the one I've just drawn, and the point over here, assume that they're a reflection over y equals x, are going to be equal. You can divide it this way, or you can have a square that's on the line y equals x. And then when you have this point on the line in the middle of the box, you actually have a function value at this point that is 0. as I was saying before, there are the two methods of dividing up the regions. One is where you have a single box on the line y equals x, and you have one region that is one value, and then another region which is the same amount, the function value, but a different sign. So they essentially cancel each other out. And then another option is you still have that y equals x line, but now the boxes are off of y equals x, and you have one on the upper left and on the lower right, and one is one value, and the other one has the same function value, just a different sign again, and they cancel each other out. So taking the method off of the y equals x line, right, we have two boxes that cancel each other out. So essentially, the Riemann sum approaches 0. But the problem is we have to be careful for when we have a box that's off of the origin, 0, 0, right? With the first method where it was just the box and it's on the y equals x line. So in a little visualizing it, we would have this box, right, and it'd be bounded by the y and the x-axis, and of course you have the y equals x line. You have some point a, comma a that you pick right in the middle if you want, and then of course we have to focus on 0, 0. For the function value on this point, it will be 0 as well. We see that the Riemann sum will approach a smaller and smaller amount because you'll have one part that is a function value that is greater than 0 and another part that is the same function value except with an opposite sign, and they cancel each other out. So the Riemann sum not only approaches anything and is always constant to 0, if we divide this square in a uniform way with the midpoint rule, that's how it's going to work. So based on this, we can say, and we're going to do a little Riemann sum, n is n, right? And we're not going to have the n or the m anymore because we're using uniform partitions. And of course we have k, which is x and j. So we have f of x, kj, star, y of k of j, star, multiplied by delta a, kj, right? And that equals 0, right? And we try to partition this method number 2, which is similar to the first in that there are usual uniform partitions of each of the sides, except there is a difference. Take the method with the boxes off of the line y equals x. Now moving on from the fact that the two boxes off the y equals x equals 0, right? If we just take one of those boxes, in this case I'm going to take the lower right, and we bound this on the y and x graph, right? And we have some point x1, and we have the origin, right? And we're going to do y1. We're not going to have y1 in this. I'm going to choose this point x1, and that we're going to label it so x2 star, right, equals x1. And so we're going to say y2 star equals 0, right, because we're not doing y1, or it's approaching 0. And we're going to compute the function value for that point. So we're going to take the example from before, you know, the one where it was x minus y over x plus y cubed, then dA, double integral r, right? And so we're going to compute the function value. So f equals x1 minus 0, and then we're going to have x1 cubed, because the y is 0, so we don't have to worry about that, and the bottom was cubed. and that's going to equal 1 over x1 squared. Now, if we go back to the Riemann sum before, as we were showing, everything is 0 except for the one thing right on the corner of that box. So the right corner, right here, everything is 0 except for that one point that we've chosen. And the reason why is if we take that little nice equation, you know, f of x of k of j star, y k of j star, delta a kj, and that equals 1 over x1 squared, right? And now we're multiplying it by x1 squared. It's going to equal 1. The entire Riemann sum is 1, and it remains 1 all the time if you keep dividing this way. So there's two different ways to approach this, and we could go further and further, but we've seen so far how choice affects the sum. In one method we'd get 0, and in the other one we're getting 1. So with the double integral, what's really being introduced is the idea of volume, and one way that I've already shown is visualizing the volume has parts that go up and reach some height of the function. So here we have just this plane that the boxes will exist on, and of course we have the points, right? You know, always with the choice of whatever point you'd like to start off with. And just recapping the boxes, one is, you know, you have the box and it comes up, it's very small, and it comes up from the point to some height of this function f that we have, right? And that's just, it's going up, reaching some point, has a volume, and we work off of that. Another method would be something that we've seen in class, is where we take a solid, any sort of solid that you want. It'd be recommended to be irregular because that's the point of this. You're going through the trouble to use multivariables for it to be irregular and for you to have a choice of partitions and points and for the functions to be irregular. So you could use single variables, which we've done in class, and then you'll get very regular geometric shapes, which is all good and nice and fine, but when you want to move into more complex objects, then you have to start getting more complex with the math, and you have to do multivariables. Right now we're just doing 2, x and y, but you can move into 3. So getting back to the solid, we have this random shape, and we're going to have it about the x-axis. And we're going to have it from x equals a to x equals b. So we have this shape with delta x, and we also have an area of a of x. And as we've seen, we can do it with a single variable where volume equals the integral from a to b of a of x dx. The part that we want to move towards, though, is combining these two methods. So what we have is you'd want to make a box, and I'm going to make its top curved, and you'll find out why in a bit. Forgive my little drawing. We have a curved top, fairly regular bottom, so it's straight. So instead of just being a box, now we have some shape other than a box. We have where we could bound this by the x and the y-axis, and then it's some irregular function that has a curve to it at the top. So it's no longer just a building or a rectangle or something regular. Now we're getting into something a bit different. And now we have this shape, and essentially it's the building going up to the function. And instead of leaving it there, we take a cross section, right? You have this cross section, and I'm just going to draw that. And we have a solid and a graph of a function, and I'm going to label the x and the y and also the z. And z equals function x f of x of y. And we gave this box a little area to the top, so it's more of an uneven cylinder object rather than a regular box. And we have the cross section, and we're going down the y. Right now, we could treat the area using a single integral like in that second method. So we have a of x from c to d, since I didn't label that, but c to d, since that's what we've been using this whole time. And we're along the y, and we have f of x of y of dy, right? And essentially, we're treating x as constant, right? And we're integrating with respect to y. So if we have x1 and we integrate with respect to y, and then we have x2 and we integrate with respect to y, we're going to have two different values. It's going to change based on where we start with x. x1, x2, x3, keep on going all the way to x to n. Whatever you want to do, it's going to change. And we have a of x equals integral c to d, f of x of y, and y dy. But the great thing is that we can also do it another way. So we have our box again. And this time, instead of along the y, we're going to go along the x, right? Let me just label my little axes z, and I'm going to try to do perspective. And this time, instead of the piece going along the y, we're going to go along the x. So it looks a bit different, the slice. The cross-section looks different, because now we're moving this way instead of this way, right? And this time we're treating y as a constant, and integrating with respect to x, and we're going from a to b, because it's always been so far x equals a, x equals b, and then y equals c, y equals d. What we should get is that both ax and by are the same, because it's the same solid, it's the same area, it's the same cross-section. Now we're just going, instead of over along the y, we're going along the x. So we should have the same, except slightly different equation. So we'll do b of y equals a to b, integral from a to b, f of x of y, and we treat y as constant, so we do dx, integrating with respect to x. So if we accept that the a of x and the b of y are the same, what we should get then is that the integral a to b of a of x dx, which is the single variable volume, equals from c to d by dy. And what we've spent this whole time explaining is essentially Fubini's theorem, because that's the conclusion he draws, is that we can go either way, and that you can have whatever choice you want. And as I showed in the beginning, we have that box, x equals a, x equals b, y equals c, y equals d. And it's very important that we understand that we can take it by parts, and that we can do it along the x, and that we can do it along the y. Because Fubini's theorem involves two variables, and it has the iterated integral, which is the double integral. And Fubini's theorem looks like integral a from b, c to d, f of x of y, dy, dx. It's essentially a combination of those two equations that we just found. And we're taking it by parts. So we're going from a to b, and we're treating x as a constant, and we integrate with respect to y. And then we go from c to d, and we treat the y as a constant, and then we integrate it with respect to x. And you don't have to do it in that order. You could do it c, d, a, b, right, f of x of y, dx,
dy. You can switch them. They're, we accepted the fact that they both should equal each other no matter which way you go. If you go along the y first or the x first, you should essentially get the same answer at the end. So the full version of Fubini's theorem is stated in this way, and an even simpler version is to use region R and the area. So you have symbol for the region R, which would be the AB and then the CD, AB along X, CD along the Y, f of X of Y, dA, right, and that would be the simplest form of Fubini's theorem.
So what are the pros and cons of additive manufacturing? Before I get into any lists, I'd just like to point out that 3D printers are self-replicating. What that means is, after building the first printer, it is then able to print out the parts necessary for its construction indefinitely, or at least until it runs out of materials out of which the parts are made. Besides being able to self-replicate, the multitude of materials that can be used in additive manufacturing are ever increasing, creating some interesting possibilities for printable objects. Pizza, anyone?
It's tough to get a pizza delivered to Mars. Instead, NASA is developing a 3D printer capable of instantly materializing food. Quartz reports NASA is in partnership with Systems and Materials Research Corporation to develop a 3D printer that could print food for astronauts. The company owner says he's already printed chocolate, so creating a device to print other foods isn't out of the question. NASA is reportedly giving the company a 6-month, $125,000 grant to work on the project. The concept is still in the works, but it will reportedly involve adding cartridges filled with powders, oils, and nutrients into a printer. The machine could then create nutritionally balanced meals.
Yes, that's right. Your dreams about printing food whenever you want may become a reality in the near future. Outside of the food industry, the wide variety of materials used for printing 3D objects means that before long, if you need, say, a liver or a kidney, you may be able to order a 3D printed organ.
And that's what we did for this piece of muscle. This is actually showing a piece of muscle and how we go through the structures to actually engineer the muscle. We take the cells, we expand them, we place the cells on the scaffold, and we then place the scaffold back into the patient. But actually, before placing the scaffold to the patient, we actually exercise it. We want to make sure that we condition this muscle so that it knows what to do once we put it into the patient. That's what you're seeing here. You're seeing this muscle bioreactor actually exercising the muscle back and forth. Okay, these are flat structures that we see here, the muscle. What about other structures? This is actually an engineered blood vessel. Very similar to what we just did, but a little bit more complex. Here we take a scaffold, and we basically, scaffold can be like a piece of paper here, and we can then tubularize the scaffold. And what we do is to make a blood vessel, same strategy. We take a blood vessel is made up of 2 different cell types. We take muscle cells, we paste or coat the outside with these muscle cells. Very much like baking a layer cake, if you will. You place the muscle cells on the outside, you place the vascular blood vessel lining cells on the inside. You now have your fully seated scaffold. You're going to place this in an oven-like device. It has the same conditions as a human body, 37 degrees centigrade, 95% oxygen. You then exercise it, as what you saw on that tape. And on the right, you actually see a carotid artery that was engineered. This is actually the artery that goes from your neck to your brain. And this is an X-ray showing you the patent functional blood vessel.
Additive manufacturing also has great applicability in the field of prosthetics. Through additive manufacturing, prosthetics can be more imaginative, more personable, but they can also be scaled down. Prosthetics may be too heavy or cumbersome for a child, but through the wide variety of materials available and the actual process of additive manufacturing itself, making smaller and lighter prosthetics is a relatively simple process. 3D printing has already had a positive effect on the lives of children already.
The existing Rex is all metal parts, and it's kind of big, and Emma was too small for that. So we required something light and small that would attach to her body and go with her. So that's where we had this Stratasys 3D printing machine, and we thought, well, we could print it out for her.
And he did it, and the weight difference is significant. And for a child who only weighs 25 pounds, it makes a big difference. Whitney and Tarek put their minds together and came up with a jacket, and they would put the Rex on that, and we're on our second jacket. She outgrew the first one, and now we're on our second one. And it's still evolving. It's still growing into this incredible prosthetic that helps her to use her arms.
There is a dark side to additive manufacturing, however, but because I love Rachel Maddow so much, I'm just going to let her explain it to you for me.
It's also interesting and complicated and maybe quandary-inducing when you consider the fact that one of the things that people are already starting to build with what they call 3D printers, these home manufacturing kits where you can make anything, one of the things people are already starting to make is a gun. If you think about a gun as being kind of like a car, then the engine and the drivetrain in the car, the part of the car that makes it go, the equivalent of that in a gun is the part that's called the lower register. It's the guts of the gun, essentially. It's the part of the gun that's registered and regulated even if all the other parts of the gun can be bought, just as if they were pieces of plumbing. But the lower receiver, I said lower register before, the lower receiver is the guts of the gun. It is the heart of the thing. And people have started to make lower receivers for AK-47 style weapons at home using a file that you can download on the internet. You can actually download it right here. I have one on my computer, which makes me wonder about the next time I have one of those things where NBC comes and checks my computer. This is what happened when the folks who printed that lower receiver fitted other parts of a gun that are not regulated the way a lower receiver is, fitted other parts of a gun onto that piece that they printed with a 3D printer. This is the video they released of themselves firing bullets out of it. And as you can see, the 3D printed gun failed and busted apart after it fired about 6 rounds, which makes it, yes, a gun, but the technical term for what kind of gun it is that it is a crappy gun because it blew apart after 6 rounds. But this kind of thing is probably not going to stay a crappy gun for long, not when you can get this far with stuff that you can find around the house, right? For all the work that has gone into thinking about who is allowed to have a gun in America and where you can buy one and what kinds of guns people are allowed to have, that all kind of goes out the window if people can just download their chosen weapon at home and have it made manifest at their desk as a fully functioning real-life weapon.